Mr. Moore's math class! Good afternoon, guys, and welcome to Mr. Moore's online math classroom. That's right, we've got plenty to get through today, like we always do. We're going to be learning about how to solve maximum and minimum problems using calculus. Now, like always, make sure you grab yourself a piece of paper, a pen to jot down some notes, get your calculator ready, put your feet up on the couch, and let's get stuck straight into the lesson. Okay guys, the very first thing we're going to have a look at is solving maximum and minimum problems where the function is actually known.
Okay, so this question says, a baseball fielder throws the ball so that the equation of its path is y equals 1.5 plus x minus 0.02 x squared, where x meters is the horizontal distance travelled by the ball and y meters is the vertical height reached. Now, this is actually an example where the function is known because we've been given the function, as you can see there. So the first question says, find the value of x for which the maximum height is reached, verify that it is a maximum, and part B says find the maximum height reached. Okay, so let's go through and write out everything that we know. We know that y equals 1.5 plus x minus 0.02 x squared. We are looking for a maximum value, and for a maximum value that dy on dx is equal to 0. Because if we throw a ball, it's going to follow a path like this, and at the very top the gradient will be equal to 0, therefore dy on dx is equal to 0. Okay, so to do this question we're going to write out the equation once again, and because we're looking for a maximum we need to differentiate. When we differentiate we get x differentiated becomes 1 and negative 0.02 x squared. When we multiply the 2 by the negative 0.02 you get negative 0.04, and the x squared drop the power by 1 just gets you x. Now because we're looking for a maximum we know that dy on dx is equal to 0. Therefore substitute that in now, you get 0 equals 1 minus 0.04 x. Okay, we now need to solve for x to find the value of x where it's a maximum, so subtract 1 and divide both sides by negative 0.04. Ends up getting us a value of x equals 24.
Strike one!
Okay, I stuffed up. Really, x equals 25. Okay, so we now need to verify that it's a maximum, so we'll draw out a table like we did in the last topic, where we put 25 in the middle because we know that's its maximum, and we go 1 below and 1 above either side, so 24 and 26. Okay, so let's just double check that the gradient is actually equal to 0 at x equals 25, so we get dy on dx equals 1 minus 0.04x, substituting 25 now, simplify, 1 minus negative 0.04 times 25 is 1, therefore it's equal to 0. Okay, substituting x equals 24 now, so just written out the formula, substituting 24, and simplifying gets us an answer of 0.04. And for 26, writing out the formula, substituting 26, simplifying gets us negative 0.04. So at x equals 24, the gradient is positive, therefore it is going up. At x equals 25, the gradient is 0, therefore it is flat. And at x equals 26, the gradient is negative, therefore it is going down. As we can see here, because our turning point is reaching a maximum point, the function is a minimum at x equals 25.
Strike two!
Okay, I stuffed that one up too. The function is in fact a maximum at x equals 25. Okay, and part B says find the maximum height reached. So that just wants us to substitute x equals 25 into the how high rule, being y is equal to 1.5 plus x minus 0.02 x squared. So we just need to substitute x equals 25 into this. So you get y is equal to 1.5 plus 25 minus 0.02 25 squared. And this gets us an answer of 14 meters. Therefore, the maximum height reached by the ball is 15 meters.
Strike three!
Ah, damn, 14. I meant 14 meters. Therefore, the maximum height reached by the ball is 14 meters.
You're out of here! Okay, it's all well and good that we know the rule of the function, but sometimes they're that stingy they won't even give us that much information.
Hey Tom,
Yeah, man.
can we maybe make a paddock full of animals that have been hanging around the house lately?
What animals, Drew? Oh, we're from Tiger, yellow and black. Oh, we're from Tiger land. Dun, dun.
Okay, so for this worked example, Jerry wishes to fence off a paddock on a straight stretch of river so that the animals whom have been hanging around his property for the past few weeks have access to fresh water. Therefore, only 3 sides of fencing are required. That there is important, so we'll just highlight that. Now it says find the largest possible area of the paddock if 240 metres of fencing is available. So we're looking for the largest possible area if 240 metres of fencing is available. Alright, we'll write out key points just in our own words. So first being we have 3 sides of fencing. We're looking for the largest possible area, and we have 240 metres of fencing available. Okay, so it's quite obvious that we haven't actually been given an equation for this question. So this is an example where the rule or the function is not given. Right, now when we get given these types of questions, there's a few steps that we need to follow. And I'll just write these down on the left hand side of the page as we go. So step 1 is draw a diagram if necessary and write an equation linking the information. So let's draw out a picture now to represent what's actually going on. I have a river and I'm building a fence that has 3 sides, giving my paddock 4 sides, but I only need to build 3 of those sides for the fence. We'll call this length here W for width and this length here L for length. Therefore W equals width, L equals length, and of course if I find the outside distance I have P is equal to perimeter. Therefore my perimeter of fencing is P equals 2W plus L because I have 2 W's and an L. And I know that I have 240 metres of fencing, so therefore I've got 240 is equal to 2W plus L. Now I'm also wanting to find something to do with area, so I know that area is equal to L times W. We'll call the first equation equation 1 and we'll call the second equation equation 2. Now if we have a look at equation 1 we can actually rearrange that and get one of the variables on its own because you can see here that L has no coefficient, so therefore we can make L the subject. This gives us L is equal to 240 minus 2W and we'll call that equation 3. Now the second step is to identify the quantity that needs to be maximised or minimised. Now this is actually quite easy because if you have a look at the question it says find the largest possible area, so what that's actually implying is we need to find the maximum possible area. Now the third step says express the quantity as a function of one variable only. So what this means is we are going to substitute equation 3 into equation 2. So area is equal to length times width, and we know from up here that length is equal to 240 minus 2W. So instead of writing L, what we can actually write is 240 minus 2W, and we multiply that by W. Expand the brackets now and you get area is equal to 240W minus 2W squared. In the fourth step you need to differentiate, set the derivative equal to 0 and solve. Okay, so because we're trying to find the maximum area we need to differentiate the area function, so you get dA over dW is equal to 240 minus 4W, and we know for a maximum area dA over dW is equal to 0 because it's a maximum point. So substituting 0 for dA over dW gets us 0 equals 240 minus 4W. Solving for W now by taking 240 over the other side and divide by negative 4 gets us W is equal to 60. And in step 5 we need to prove that it is in fact a maximum or a minimum value. So to do that we'll draw out a table like we have done in previous questions where we put our value that we've just found in the middle and we go 1 below and 1 above. And we'll substitute these now into the gradient function. So when substituting in 59 into the gradient function you end up getting 240 minus 236, which gets us positive 4, so therefore the gradient is positive and the slope is going up. When we substitute in W equals 60 you end up getting an answer of 0, so the gradient is 0 or flat, and therefore it's flat like that. When we substitute in a value of W equals 61 we end up getting 240 minus 244, so therefore you get negative 4, so therefore the gradient is negative and is going down like so. Therefore the stationary point is a local maximum, or the area of the paddock is a maximum when W equals 60. Now step 6 says sometimes a function's maximum or minimum values occur at the extreme points of the domain, so check these also. Now because we know that the area function is a quadratic, we know that the graph is going to just go up to a maximum point and then go back down. because it's a parabola, so therefore we don't need to really worry about doing this. Step 7 says answer the question that is being asked. Well, the actual question is saying find the largest possible area of the paddock if 240 metres of fencing is available. So we're looking for the largest possible area. Therefore we need to find out what L is by substituting into equation 3. So you get L equals 240 minus 2W. Now we know W is equal to 60, so you get L is equal to 240 minus 2 times 60. L therefore is equal to 120. And we're looking for the largest possible area, so we have area is equal to length times width. Substituting those two values in now, area is equal to 60 times 120, which is equal to 7,200 meters squared. Good luck fitting that in your backyard, Jerry. And there is an 8th step where it says sketch the graph of the function if it helps to answer the question, noting any restrictions on the domain. Well, that's not really essential for this question, but sometimes you may find that it does help.
Okay guys, thank you very much for tuning into today's lesson on solving maximum and minimum problems. And in fact, it's actually the very last lesson for this topic on differentiation. Now make sure you stay tuned for the very next lesson because we're going to start a new topic called anti-differentiation. That means going the other way. Alright, so like always, make sure you say hi to your maths teacher for me. Morsey out.